Hello, I'm Professor Wood. We're going to be finding out today whether or not water can actually be on a globe. We all know that water on a flat surface will spread out over time. We'll get into that in another episode. Right now what we want to know is if water will actually fit on a globe. In front of me is a standard chicken egg. This chicken egg represents the Earth to scale of a chicken egg. Given the relative depth of the water and the mass of the Earth itself, all the oceans comprise one drop of water on a chicken egg. So we're going to put some water on a chicken egg and we're going to see whether or not the water runs off. We've all seen this experiment. This spoon represents the surface of a curved Earth. If we pour water on it, the water runs off. But that's not realistic. One other, this is just a trivia before we put water on there. If the Pacific Ocean was empty and we were going to add one drop of water and double the number of drops each time, it would take 87 times before the Pacific Ocean was close to being full. But on number 88, the Pacific Ocean would be full, but there would be sufficient water to fill the Atlantic and Indian Oceans as well. Understand something. If you're going to do flat Earth, globe Earth science, know something about science before you start. Anyone who is questioning the credentials on this, rather than me present them because you're not going to believe it, go research it. Get a book on oceanography and find out the facts. Now, let's add some water and let's see what happens. If you can see the shiny areas of the egg, this is where one drop of water has been spread over the surface. It's not running off, it's staying right in place. Again, you can see the margins of the water right there. The delineation between the delineation between where the egg is sweating because it's cold and there's humidity in the air. In fact, it's raining, and here you can see the delineation where the water has reached a point and it's not going any further. Now, some of you people are going to claim that the gravity should be pulling the water off. I want to get rid of the idea of gravity once and for all. There's no such thing as gravity, and we're not going to deal with a false religion. We'll be covering this later, but for right now, we can see that when you add the amount of water to a globe Earth, in this case a globe Earth that's the size of a chicken egg, the water does not run off as you've seen in that previous clip. Jim, are you okay? Yes, Professor, I'm fine, but can you believe that dragon just ate that egg in one swallow? No, I can't believe that. I've never seen a dragon eat an egg that fast. Thanks very much. It was delicious. Well, you've seen a real science on the globe Earth. We'll now put a drop of water on a flat Earth and see what happens. My graduate student in hydrology has just placed a drop of water on a flat surface that represents the Earth if it was laid out flat. As you can see, that drop of water is just beaded out. It's not going anywhere. The next thing we're going to do is we're going to try to spread it just a little bit. Alright, using a robotic arm, we're going to spread the water a little bit with a probe. Alright, now this is an important experiment. I'm going to explain why. As you can see, This surface area is actually a little bit larger than that of an egg, but not much. On a flat Earth, the water actually does not really spread out. It tends to congeal together. Now this is kind of interesting that it would do this, but let's understand something. There's also two different media here. The other one was a hard rock. That was the eggshell, made of calcium. This one is made of paper, and so some of the water may have absorbed into it while we were waiting for the robotic arm to spread this out. But the point being, on the round surface, the water readily spread out, whereas on a flat surface, the water really kind of congealed together. Now remember something, and this is very important. When you're talking mass, the area and that kind of thing, and you have something the size of a chicken egg in mass, and you have one drop of water which represents the ocean on it, and the ocean tends to just kind of congeal in one spot, you have a bit of a problem. And we're about to look at this in from another viewpoint. Now remember, this is our research, and you need to do this yourself at home. And we're going to do two experiments. The first is we're going to show you that we're actually placing a drop of water here. And the second, we're going to show you how water actually reacts on a flat surface and why a flat surface is somewhat disconcerting to someone that's actually doing science, or at least real science, science that can be duplicated by you, me, or anyone with a PhD. I mean, if you have an electron microscope at home, there's no reason why you can't be doing real science. We're back. Can I have the robotic arm come in here and place a drop of water so that we can see we're actually using only a drop? Alright, there we go. We have our drop of water. Having established that we are in fact actually using one drop of water both on the egg and the flat surface, we're going to move on. We're going to move on to the next experiment. Jim, I've been stealing your thunder throughout this presentation. You're the PhD hydrologist. Would you like to give the last presentation here? Thank you, Professor Wood. I would. No pun intended. In front of you is a vial, specifically a test tube. If you want to do science, you need a test tube. But we have a vial with a colored fluid in it so that it's easier to see. If you look around the edges of the glass, you'll notice that the fluid is pulled up slightly. That's called a capillary effect. And we can test that. Robotic arm, please. When this tube goes down into the fluid, water comes into it. That's called a capillary effect. There was no siphoning on this. If you'll get yourself a clear piece of plastic tubing, you can do that experiment at home. It's called the capillary effect. Now the edges rise up, and we'll get into the physics of that a little bit later. Not in this presentation, but a little bit later. If you look in the middle of the water, it's slightly depressed. That's called meniscus. That is, the water is actually concave. If you fill the water to the top of this vial and you keep adding to it, the surface tension will hold the water together. There's been a lot of discussion on that on other channels, so there's no reason to go into that. But then you have a reverse meniscus. That is, the water is beaten up. But this is just a plain meniscus. The water is pulled up against the sides of the test tube, and it's depressed in the center. Now this is going to be real important when we come to the flat Earth and why ships disappear from the bottom up. Again, our science is going to be absolutely, without a doubt, completely provable, something that anyone can do. Let's have the robotic arm. Here's our ship. It has reached the water level. On a flat Earth, as the ship sails, we've all observed that it goes down just like this until it disappears. What we're observing, and we've just proven it, is clearly that on a flat Earth, the ship disappears from the bottom up, not because water seeks its own level, but because of the meniscus. The ship is sinking from the bottom first. The other explanation, which I don't even think flat Earth people are going to go there, is that submarines have existed since ancient times in terms of Earth history. So you have a choice, guys. Either what you're seeing is the ship disappear because of a meniscus, because you haven't done your science, or we've had submarines since day one. I think the conclusion is very clear. We have submarines because we've just proven that the Earth is round.